All right, so what else do we need to stop this? All right, so let's talk about inductance.
I've got to tell you, a few weeks ago, I saw the white metal detector ad on TV. In no time at all, my local dealer had me out treasure hunting. I was finding the good stuff my first day. And the best part? You can see what's in the ground before you dig it up.
Your treasure hunting adventure can start right now. Call for your free catalog.
My wife said I needed a healthy hobby. She's proud of the weight I've lost, and really proud of this.
Call now.
Wow, that was cheesy.
I've
Cheesy and desperate. All right, so metal detectors. How they work. I guess interesting. All right, so concept of induction. Believe it or not, we've actually done this concept without you guys noticing it. In the form of transformers. It's the same idea. You got a primary coil, you got a secondary coil, except you don't have an iron core in the middle. So what's happening is you get an alternating current. So the direction as well as the value of the current varies. All right, so the current generates a magnetic field. That magnetic field is going to be a circulating magnetic field, so which means that the magnetic field is going to get intercepted by this loop. So the magnetic field created by the current is going to get intercepted by the loop. As a result, it's going to cause something called a back EMF. But that's not that important right now. All right, so current here is circulating current here is going to cause a circulating magnetic field. And then that magnetic field is going to be intercepted by the secondary coil. If the magnetic field generated by the primary coil is changing, if its value as well as the direction is changing, it's going to cause a change of flux in the secondary coil. And if you change the flux in the secondary coil, there's going to be a current in the secondary coil. That's it. So the alternating current in the primary coil is going to induce an alternating current in the secondary coil. That's the meaning of it. So the alternating current in the primary coil is going to induce current in the secondary coil. And this phenomenon is known as induction. All right, so the alternating current within the primary coil is going to create a varying magnetic field. The amount of varying magnetic field intercepted by the secondary coil is going to cause an alternating current within the secondary coil.
The most common and thorough technique is the Minesweeper. It's also the most dangerous, putting a man right in the heart of a live minefield. It's really just a supercharged metal detector, like the kind first used in World War II. The only real difference is that today's mine detector is lighter and much more sensitive.
Right now I'm clearing a path approximately 1 meter wide. This path should be wide enough to accommodate a platoon of Marines.
Slowly, the sweeper moves forward until...
What I'm doing right here is I'm finding the boundary of my signal. I've picked something up in the deck. I'm just marking it so that my prober can come up.
What do you got?
I've got my left letter limit. There's a scratch in the deck here. You see it?
Yes.
Using a probe, the combat engineer delicately explores for any hard contact. When he finds something, the soil is brushed away.
You've got some green plastic down here.
When the mine's uncovered, a TNT charge is placed.
oh, smoke.
And detonated. The most common and thorough technique is the Minesweeper. It's also the most dangerous.
All right, so the question is, how does that work? All right, guys, I'm going to give you like a minute to figure this out, in case there's a test question like this. How does it work? I don't know. Okay, 30 seconds in. All right, so focus on the receiving coil and notice the orientation of the receiving coil relative to the transmitting coil. Okay, why did they put them at right angles to each other? All right, so mentally try to figure that out. All right, so this orientation is crucial for the setup. All right, so just think about it. Just try to figure it out for yourself first before I explain it. Okay. Okay, so the transmitting coil obviously is important in terms of generating the magnetic field. Okay. In the transmitting coil, you have the alternating current. I know that for various reasons. I'm looking at the arrows, which means that it's oscillating back and forth. The current is going this way and that way. So the alternating current is going to cause a varying magnetic field. And then you have something buried in the ground, in essence. In this case, you got the gold coins. I don't care. Any metal will do. It could be copper. It could be aluminum. It doesn't matter. The whole idea is the reason why you have the varying magnetic field, because if you're varying the strength of the magnetic field intercepted by any metal, it's going to cause eddy currents. And eddy currents will obviously, if you keep varying the direction, if you vary the strength as well as the direction of the magnetic field, inside any sort of metal piece is going to cause eddy currents. These eddy currents will be alternating currents. Obviously, the alternating current is going to generate, once again, a very magnetic field. And if the receiving coil, which is set 90 degrees to this one, the amount of magnetic field intercepted by this one, if it's varying, it's going to cause a current, alternating current here. As soon as there's current in the receiving coil, obviously you will hear the beep. So my question to you was, why set this at 90 degrees to this one? All right, so you're thinking, oh, so that it can actually intercept the magnetic field generated by the buried coins? Yeah, not quite. Okay, you have to set this 90 degrees to this one because you don't want to intercept any of the varying magnetic field generated by the transmitting coil. All right, you don't want to do that because if this starts intercepting the magnetic field generated by this one, there's always the idea you will end up, this is going to keep beeping all the time. All right, so it's going to defeat your purpose. All right, so once again, let's get back to the story. You got that alternator here. Alternator is going to generate your magnetic field. All right, it's better.
Yes.
Very cool. Yours has my points. All right, so alternating current causes a very magnetic field. And when that very magnetic field is intercepted by the area of the secondary loop, is going to have alternating current. All right, so just vary the flux in the secondary loop. Obviously, it's going to cause an alternating current inside the secondary loop. All right, so now now that we understand the conceptual a little bit, let's come up with a mathematical way of expressing it. All right, so the alternating current here, forget the alternating current just for now. The current here is going to cause a circulating magnetic field, right? And that circulating magnetic field is going to get intercepted by the secondary core. All right, I love the setup of this one. It's very simple. It's elegant. All right, so what this means is the current within the primary is going to be responsible for the flux in the secondary. All right, it's straightforward. It's beautiful. You got current here. The current generates magnetism, and that magnetism gets intercepted by the area of the second coil. This is exactly what that means. Okay, we're not varying the current. We're not varying the flux within the secondary. This really captures the meaning of it. It's straightforward. Current is going to be responsible. Current in the primary is responsible for the flux in the secondary. All right, and obviously, this represents the flux through a single loop. If you have multiple loops, obviously this current is going to be responsible for the flux through multiple loops. That's what it means. And then the flux through multiple loops in the secondary is going to be proportional to the current within the primary. And then obviously this is proportionality. You know, to get rid of proportionality, use a proportionality constant. I just hate using the term proportionality constant because these things mean something in physics. This proportionality constant, the term that I hate using, I will keep using it because I hate using it. Because I'm looking for a better way of explaining it. And these things are just so incredibly abstract. And they're so abstract, I don't usually talk about this to non-technical people. So we'll just go with what's in the textbook. Okay, so this is known as mutual inductance. All right, so M means mutual inductance. All right, so I'm not going to chicken out. I'm just going to go back and then battle this a little bit more because I like to come up with the meaning of these things. Okay, let's focus on knowledge before we talk about some a little bit more philosophical. M means mutual inductance. H is the unit. It stands for Henry. And Henry is the name of someone, obviously. Why not use Faraday? Because it's Faraday's law. Everything is the extension of the Faraday's law. Well, obviously, we don't use Faraday because it got used up accidentally while we were dealing with the capacitors. I don't know why all of a sudden they decided to use his name. In his honor, they decided to the capacitance became Farad. I think the inductance would have been better for Farad. Henry is another guy, Rochester, New York, high school teacher, instructor. And then this is the guy who actually discovered the electromotor in essence. So in his honor, they decided, okay, so let's just give him something. So that becomes a recognition. So what does the mutual inductance represent? The mutual inductance, in essence, tells you how much of a flux you can induce in the secondary by the amount of current that you have here. So the fraction of that current is going to be responsible of the amount of flux that you're inducing on the secondary. All right, so this is like some kind of multiplication factor. In essence. I cannot think of anything really good to say on that one because these lectures, if I'm lucky, I'm giving these lectures once a year. These are not like the art school lectures. All right, so okay, moving forward. So we set it up. This was a nice setup. The current in the primary is going to be responsible for this flux in the secondary. The current in the primary is going to be responsible for flux in the secondary for each and every single loop. So with that, that's what it means. And then you have some kind of multiplication factor, and this multiplication factor is like almost like a magnification factor. So this amount of current can cause this amount of flux in the secondary. That's what it means. This amount of current probably can cause this amount of flux, like 3 times the value of the current, half a times the value of the current. It's just some kind of multiplication factor that you're looking at. All right, so now let's get back to the story. We came up with our main equation, right? So here's what I'm doing. We're varying the current in the primary right now, which means that not only are we varying the direction of the current in the primary, but also we are changing this value of the current in the primary. So any variation of the current in the primary, I'm talking about the value as well as the direction, is going to end up causing a change in flux in the secondary, right? Through each and every single loop that you have. So there's going to be an electromotive force in the secondary. Okay. One of the things that I want you to notice, and this becomes important when you are doing the multiple choice section of the test, the change in current in the primary and the change in electromotive force and the current in the secondary. Notice that current in the primary and the current in the secondary may or may not be moving in the same direction. All right, so watch out for that one. All right, the current in the primary and the current in the secondary, they're not going to be in the same direction. They're going to have the same frequency and everything else, but they are not necessarily moving in the same direction. That's what it means. So here's the electromotive force generated inside the secondary, all right, which is going to be caused by the current within the primary, changing current within the primary, multiplied by some kind of a magnification factor, which is known as mutual inductance. So it's going to give you the change in flux within the secondary, change in flux within the secondary for each and every single loop. It's going to be responsible for the electromotive force in the secondary. Man, this was a long explanation, but that's in essence, this is what we came up with conceptually, and mathematics beautifully captures it. All right, so what I'm looking at is the value of the current goes up and down. You change the flux within the secondary, changing flux within the, you vary the current within the primary, and variation of the current within the primary is going to change the flux within the secondary, and the change in flux within the secondary is going to cause an electromotive force in the secondary, blah, blah, blah. All right, this is how it works out.